Hi, welcome to my channel. This is Ian Ageshwara, working as Associate Professor in the Department of CSC. In the last video, I discussed about the algorithm properties or criteria of an algorithm. In this video, I am going to explain performance analysis. Performance analysis. Generally, the analyzing algorithm is loosely divided or categorized into two different categories here. One is a priori estimation. So we call it as performance analysis, and another one is a posteriori testing, that is called as performance measurement. I will explain one by one. What is priori means before. Priori means before. Okay. So estimation means, so before converting algorithm into program, we are going to analyze algorithm for calculating time and space. Okay, na? That's why we call it as priori estimation. We are estimating by using pen and paper or pencil and paper. We are estimating algorithm, time complexity and space complexity, because analysis ultimate aim is calculating how much time is required to solve problem and how much space is required to store the program and data. Okay, so this is called priori estimation. Priori means before converting algorithm into program, we are analyzing algorithm. In the first step, we are analyzing algorithm. That's why we call it as performance analysis. We are analyzing algorithm. That's why we call it as performance analysis. So this is the first step is machine independent. Because we are not using machine, we are simply analyzing algorithm. That's why we call it as priori estimation. What about second one? Second one is posteriori testing. What do you mean by posteriori? After. Posteriori means after. So after converting algorithm into program, we are using machine for testing that particular program. So that's why we call that particular step as posteriori testing, or we can also call it as performance measurement, because we are measuring actual time required to solve the problem and actual space that is required to store program and data. That's why we call it as performance measurement. First step is called performance analysis or priori estimation, because we are estimating time and space complexities based on algorithm. Here we are measuring actual statistics of the program, required statistics. That's why we call it as performance measurement, or we can also call it as posteriori testing, because we are testing the program on machine. So that's why second step is machine dependent. Second step is machine dependent. But ultimately, what is the use of applying analysis? What is the target of applying analysis? Generally, we are applying analysis on either algorithm or program to find how much time is required to solve the problem, and how much space is required by program as well as data for storing. So that's why we call it as time complexity. We call first step as time complexity, and second step is called as space complexity. So in time complexity, we can calculate the total time needed to solve the problem, and in second step, we are going to calculate the total space required to store the program and store the data and for running. Okay, so these two are the goals of performance analysis or performance measurement. Performance analysis calculates time complexity, space complexity manually or physically on algorithm, and performance measurement is calculating both time and space complexity on program using machine. So I have already told, so that's why first step is machine independent, second step is machine dependent. In this video, I am going to explain space complexity first. After that, I will explain time complexity. Then what do you mean by space complexity? I have already told you the exam definition. Total space needed to store total space needed to store and run an algorithm. Total space needed to store and run. So here the total space needed is the space needed by program, the space needed by program, and the space needed by data. So we need to calculate space needed by program, we need to calculate space needed by the data. So once after calculating space needed by program and data, if you combine these two, we get the total space complexity. But if you observe algorithm or program, that algorithm may be containing two different parts. So one particular part related space is allocated at the compilation time itself, and another particular part is required space is allocated by the compiler at the running time, because at the time of compilation, compiler won't know the size of the particular variable, and but for some variables the compiler may know the required space at compilation time. So based on these two requirements, we can divide the parameters that are available in program into two parts. One is fixed path or fixed space. Second one is variable path or variable space. Now we'll explain one by one. Fixed path or fixed space, and second one is variable path or variable space. But as a programmer or developer, we have to identify which parameters are coming under fixed path and which parameters are coming under variable path. Now I will show you based on algorithm or program. I will show you here which are the items coming under fixed path. Okay. So what I told you, fixed path means at the compilation time, at the compilation time itself, if the compiler allocates space, at the compilation time itself, if compiler allocates space, any parameter you can consider, any parameter in the program or algorithm, if that particular parameter related space is allocated at compilation time itself, then that particular parameter is coming under fixed path. Variable path means at the compilation time, compiler doesn't know how much space is required to store the parameter. So such type of parameters are coming under variable path, because at the time of running or execution only compiler can allocate space. So that's why those parameters are treated as variable space or variable path related parameters. Now I'll give examples here, which are the parameters coming under fixed path. Is it clear? What is fixed path? We can easily recognize fixed path in the program or algorithm like this. If compiler is allocating the required space at compilation time, then we must take that particular space under fixed path. If the compiler allocating required space at running time or execution time, then that particular space is coming under variable path. Then I will show you. So based on these parameters, we can easily understand. Okay. So first one is code space. What is code space? Code space means program or algorithm space. Either program or algorithm space. Code space means program or algorithm space. Why this particular code space is coming under fixed path? This is the first item under fixed path, because during running time, please remember, of course at the compilation time we can change the code, we can change the length of the code also, but once compilation is success, but during running time, nothing is there in our hands. We cannot change code length. Just as a programmer, we can give the required data through keyboard, or processor may take the required data from the memory, from any specified file location. Okay, so that's why we take code space as fixed. Code space is fixed. During running time we cannot change anything. So that's why code space is coming under fixed part. Second one is simple variables. Simple variable space is also coming under fixed part, because simple variables in the program like int a, b, c, or float a, b, c, char a, b, c, like that. Once you include this a, b, c during compilation time, once compiler reaches this particular step in compilation process, automatically the compiler allocates one empty cell for this, one empty cell for this, one empty cell for this, or one word. Empty cell or one word for this, one word for this, and one word for this. The word sizes or empty cell size is depending on data type. Okay, na? But we are talking the space required is word terms. Okay, so E is requiring one word, but this word size is 2 bytes because the data type item is integer. B is also allocated with one word or one empty cell, but empty cell size is 2 bytes because all these items are of type integer. And C is also allocated with one word, but that word size is integer. Okay, na? So this is about simple variables, because the required space, the space required by ABC, or the required space by this particular statement 3 variables are allocated by the compiler at compilation time itself. I have already given if compiler is allocating space at compilation time, then this item is coming under fixed path. Okay. And third one is, sometimes our program may use constants. Some programs may use constants. Constant means, as a programmer, we are fixing that particular value for the entire program as constant or fixed. So that's why at the compilation time itself, compiler knows how much space is required. So this is also coming under fixed path. And last item is component or compound variable. Component or compound variable. But here we have to remember, compound or component means combination. Compound or component means combination. I will tell you like this. Int, suppose a of 10. So what is the information known here? So for any component or compound variable, Component or compound means combination of two items. One is array name, another one is array size. That's why we treat this particular item or variable as component or compound variable. But if we observe this declaration int a of 10, the size of that particular array is known at compilation time, because here the component and compound variable whose size is known here, then automatically at the compilation time the compiler simply allocates 10 empty cells or 10 words to this particular array, because we are making this particular array size in advance to the program or algorithm. So automatically the compiler will allocate 10 empty cells. Then what is the cell size now? Each cell size is 2 bytes, because each item in the array is of type integer. Or if you write float, then each array element size is 4 bytes. If you write character char a of 10, then each character size is 1 byte. So like that component and compound variables, but whose size is fixed, is also coming under fixed part, because all these items, if we observe all these items, those items required space is allocated at compilation time itself. Okay. Next one is variable part. So as a programmer, we have to also identify which items are coming under variable part. Please remember here, the variable part means that the space required is known at running time or execution time. At the time of execution or running, if the space required by that particular parameter is allocated by the compiler, if compiler allocates the required space at execution time or running time, generally we bring that particular variable or parameter under variable part. Then I will tell you. First one is, take the last item, component or compound variable. Component of compound variable, but whose size known at running time, but whose size known at execution time. Like int a of n, we don't know n value. So during compilation time, compiler doesn't know the n value, but it process, because syntactically this int space a of n followed by semicolon is syntactically correct. Then the compiler processes this particular statement as legal statement at the time of compilation, but it cannot allocate space because this n is unknown. Okay, so this n value is made available at running time only. So during running time, as a programmer, we can enter n value. If you enter n as 10, then 10 cells are allocated at running time. If you enter n as 100, then 100 cells are allocated at running time. That's why the component are compound variables, but whose size known at running time. Then this particular parameter is coming under variable part. And second one is reference variables. Reference variables are used for referring different data type items. So one particular function, that reference variable may be used for referring integer, that same variable may be used for referring floating point, and the same variable may be used for referring character. So that's why this reference variable size is varying based on the reference parameter. So that's why this is also coming under variable part. And third one is very, very important one, recursion stack space. So this recursion stack space is also coming under variable part, because we don't know how many times that particular recursive procedure is called. Okay, generally the recursive procedure is using stack as a data structure for calculating or manipulating or applying operations. So recursion is a procedure which is used for using stack as a data structure for performing operations. But recursion stack space is depending on three important parameters. I will show you in examples. What are those three? How we can recognize those three parameters? So those three are formal parameter. I will show you an example which is formal, which is local variable, which is return address. Second one is local variable, and third one is return address. So the stack space is depending on these three items. So stack space is depending on these three items, but we don't know how many times that particular function is called by itself. So that's why that is known at running time only. That particular one is known at running time. But each recursive call, these are the minimum locations required. These are the minimum locations required because each recursive call is using one formal parameter, each recursive call is using one local variable, and that recursive call is also using return, which must return the result back to its parent function. So that's why these three are default items which are required for storing the items in each recursive call. Then based on number of repetitions, we can say that those number of repetitions into 3 is minimum. Okay, so this is about variable part. Now I will show you examples for calculating space complexity. Generally, if you observe your programs, any program, that program may be simple program without having an iterative statements, or your program may contain iterative statements, or your program may contain recursive statements. Generally, these are the nature of the statements which are involved in any program. Either we, without involving iterative and recursion, we can write the program. That program is called simple program. Or we may use iterative statements for writing the program. Then that particular program may be called iterative program. Or sometimes we may involve recursive statements also. Then that particular program is called recursive program. So these are only the variety of statements which are going to involve in your program. Okay, so based on this, I will explain first by taking simple program without involving iterations and recursions, what is the time space complexity, and second one is iterative statements, third one is recursive statements. But before going to see this iterative or recursive and simple programs, suppose if you want to solve any problem, I have already told the total space needed by that particular problem is equal to fixed part is treated as constant and variable part is represented like this. This is variable part. This is variable part. Variable part, and first one is fixed part, so this is constant. At the time of compilation, the compiler is allocating space. That's why we treat it as constant. That is not depending on any characteristic. But yes, this variable part is depending on instance characteristics. Instance characteristics. I will tell you what are instances and what are characteristics. Instant characteristics here. Now I will write what are instances to any problem. What are the characteristics? Instances and characteristics. Characteristics. What are instances to any problem? Even you design any machine, what are the instances here? Even you write any program or algorithm, what are the instances here? There are two instances. One is input, second one is output. These two are the instances. Okay, na? After designing algorithm or after writing program, we are supposed to give one particular legal input or known input, and we need to test the program. So this particular one is called as one instance. Once after giving input, that particular input may be processed by program. So we ultimately expect one output. Once after getting that output, we say that whether a program is working properly or not. So that's why we treat input is one instance to algorithm or program, and output is another instance to algorithm or program. But what are the characteristics here? Two characteristics are there. One is size, another one is number. I will relate these two to instances. Okay, na? So combinedly call them as instance characteristics. Combinedly call these items as instance characteristics because the total space, running space is depending on instance characteristics. I will show you one example here. After that, I will move to these three examples. Okay, na? Then what are the instance characteristics now? Combine these two items. Number of inputs and size of each input. This is the instance characteristics of input. What about instance characteristics of output? Number of outputs and size of each output. Number of outputs and size of each output. I will relate it to example. Okay, now suppose even earlier we seen compound variable. Suppose int a of n. Compound variable is int a of n. Suppose if you write n equal to 10. If you write n equal at one instance, if you give n as 10, then how many cells are required to store this? 10 cells, 10 words. Suppose if you at the next instance, if you give 100 as input, then here the number of cells required to store array is 100. Okay, na? Suppose if you want to add all array elements, if you write a program to add n array elements, so in this case, if you enter n as 10, then which requires only 10 cells. But at the next instance, if you enter n as 100, this particular instance is requiring 100. Means the space required at running time is varying. Suppose based on inputs, sometimes the number of outputs may be varying. Based on inputs, sometimes based on some programs, the number of outputs may be varying. That's why This particular running time space is depending on instance character 6. Is it clear now? What are the instances? Input and output are instances to any program or any algorithm, and character 6 are size and number. If we combine these two, we get instance character 6 now. Now, first instance related character 6 are number of inputs and size of the input, each input. And second instance related character 6 are number of outputs and size of the each output. So based on that, this running time, the running time related space is varying. That's why we must concentrate on this one. We must concentrate on this one, because anyway, this particular space is treated as a constant part. Anyway, we need to calculate both the items. Okay, na? First item is at the compilation time itself, we get the total space required to store the constant part. But at the running time only, we know the running time parameters related space. Okay, but this running time space complexity or variable part or variable space is depending on instance character 6 now. So based on number of inputs and size of each input, those number of cells and bytes are allocated. Okay, na? Suppose data type is integer. If you enter n as 10, then 10 empty words or empty cells are allocated, but each cell size is 2 bytes. Suppose if you enter n as 100, then 100 cells are required to store array elements, but each word size is 2 bytes. Suppose if you change it to float, the same. If you enter n as 10, then 10 arrays words, 10 empty cells or 10 words are allocated. Each word size should be 4 bytes. And if n equal to 100, see here. So based on entered input, based on entered value, the space is varying. Based on entered value, at the running time, the space is varying. That's why the running time or variable part is depending on instance character 6. Remember these two instances and character 6. If we combine these two items and these two items, we get instance character 6 now. Once again, I will pronounce instance character 6. Instances are input and output. Character 6 are size and number. And if we combine these two items, we get instance character 6 now. Input related character 6 are in number of inputs and size of the each input. Output related character 6 are number of outputs and size of the each output. Here I am considering 3 examples now. I have already told this is simplest procedure, which is not involved with any iterative procedure or any recursive procedure. Now here I am involving simple recursion. Simple iteration means one loop and one statement within that loop. That's why we call it as simple iterative, simplest iterative procedure. Simple iterative procedure. Okay, na? Simple iterative procedure. This one is simple recursive procedure. Simple recursive procedure, because only one recursive call, one function, that function is repeated repeatedly, and only one statement is going to be executed. Now I will explain one by one. Now first consider simplest program. Simplest means no for loop and no recursive call is there in this particular one. Only one statement is there. Then here SP is 0. Because there is no instance that is playing here. Only constants, only ABCD are appearing. Those ABCD are treated as simplest variables. So that's why only constant part is there. That constant part is how many variables are there? 4 variables. Then 4 words are required. 4 words are required. So based on ABCD data types, those number of bytes may be allocated. Suppose ABCD are float. Then 4 into 4 bytes are allocated, because 4 variables are there. Then each variable is requiring 4 bytes. Then 4 into 4, 16 bytes are allocated. Suppose ABCD are of type integer, then 4 into integer size is 2 bytes. Then 4 into 2, 8 bytes are allocated to this particular program, because there is no instance playing here. Only simple variables are there. So those simple variables are requiring constant space. So if there is no iteration and there is no recursion in any program, simply we treat it as simplest program now. So that simplest program is requiring constant time. There is no variable time playing in that particular program. Is it clear in that? Okay. So this is simplest. Only simple variables are involved. Simple variables are requiring constant space. Then variable part is 0. There is no instance character 6 now. So size of the input and number of inputs are not playing here. Only simple variables are there. Those simple variables related space gathering is our duty. How many number of variables are there? Simply count those number of variables, and based on data type item, we say that those number of items into integer means 2, floating point means 4, character means 1. So that much memory is required. Okay, that is simplest program. Now second program is simplest iterative program. and in simplest iterative program and simplest recursive program, I am going to calculate sum of all the given n array elements. Sum of all given n array elements now. Okay, na? So for calculating sum of all given array elements, first initialize sum at 0. First initialize sum at 0. Next, extract one by one element and add that particular element to previous sum. Initially, at I equal to 1, we can extract first element. At I equal to 1, we can extract first element. So at I equal to 1, we can extract first element. So that first element is added to the previous sum. Initial sum is 0, then 0 plus first element sum. Okay, that is updated as updated sum. At I equal to 2, we can extract a of 2 and we can add that particular a of 2 to previous sum and so on. Once for loop is executed or for loop execution is over, we get total sum at left side part. Then our duty is return that particular sum to the called function or its parent function. Okay, this is the program. We know already that this is the simple algorithm. But we need to identify which items are coming under fixed part, which items are coming under variable part. The first, completely observe the program. One simple variable is s. Another simple variable is I. And third simple variable is n. Other than this, is there any other variable here? Okay. So s, I and n are simple variables. These simple variables are requiring one word each. Each simple variable is requiring one word each. Then these three are requiring 3 words. This is constant. Then what is variable part now? Array is variable part. So this array required space is depending on n. If you enter n as 10, then a of 10, it becomes a of 10, then 10 memory cells are required. If you enter n as 100, then a of 100, array structure becomes a of 100, then the compiler allocates 100 empty cells to the particular array. Is it clear? Okay. So here arrays for loop is varying from 1 to n. Then minimum n cells are required to store n elements. So array is requiring n cells. Is there any other item here? Here problem instance is depending on n. N is the instance now. The entire program instance or problem instance is depending on n. N is the instance now. So during running time only, as a programmer, we can make n value available to program or algorithm. So the compiler can allocate the required space at running time only. So that's why the space required by array is coming under variable part, and the space required by s, I and n are coming under fixed part. So how many cells are required now? N plus 3. N is the array required space, and 3 are 1 each by s, I and n. S is requiring 1 word or 1 empty cell, I is requiring 1 word or 1 empty cell, and n is requiring 1 word or 1 empty cell. Then those 3 are here, and n is array required space. So totally n plus 3 cells are required by this particular simplest iterative procedure. Is it clear now? But we cannot always expect one for loop or one array or one statement within that for loop. So we can generalize the space required by this. So the space required by any problem of size n, or we can write it like this. Already I wrote procedure name. S sum of n array elements is always greater than or equal to how much? N plus 3. This n plus 3 is the simplest iterative procedure, but we cannot always expect one for loop or one statement or one array in the program. But if one for loop is there, only one array is involved, then minimum number of cells required are n plus 3. So I am going to generalize here, because any iterative procedure is minimum requiring n plus 3 cells. So this is about simplest iterative procedure space complexity, and this one is simplest program space complexity. Then what about recursion now? Is it clear this? So simple iterative procedure is requiring these number of cells. N is for array, storing array elements, and 3 is for storing s. One cell is for s, one cell is for I, one cell is for n. So totally n plus 3 cells are required for this program or this algorithm. But what about other iterative procedures? We are treating it as simplest. Simplest means one for loop and one statement and one array. But we cannot always expect one for loop, one statement and one array. So that's why we are considering it as minimum space. That's why we can write relationship as s sum of n. The space needed by any iterative procedure sum with n numbers or of n numbers or n elements is minimum n plus 3. Like that we can write. Suppose if you move to simplest recursive procedure. In simplest recursive procedure, only one statement is there in true or false. One statement is there in true or false. So this is if n less than or equal to 0 means all items I've already considered, then which returns 0. Otherwise, at n which extracts a of n outside and which immediately calls the same procedure on remaining n minus 1 elements. And again this procedure becomes a comma n minus 1. So here again we need to return R sum of a comma n minus 2. At that particular moment we extract a of n minus 1. Like that, at each recursive call one element will be extracted and that particular element is added to the unknown sum. Like that, this particular procedure will be repeated. So at the n we need to repeat the procedure. At n minus 1 we need to repeat the procedure. At n minus 2 we need to repeat the procedure. At n minus n also we need to repeat the procedure. So at n minus 1 dot so on 1 at 0 also, because at 0 only compiler knows there is no element remain for consideration. Okay, at that moment which returns 0. Then how many times the recursive procedure will be called? How many times recursive procedure will be called? One is at 10, another one is at 10 minus 1, another one is at 10 minus 2, so on up to 1. So up to this is n plus at 0 also we need to consider. So totally n plus 1 repetitions are there. So this particular recursive procedure called by n plus 1. But as a programmer, our duty is finding how much space is required by each recursive call. In iteration, no intermediate result is available in the computer memory. Once for loop is exhausted, simply we get only one result. We cannot extract at I equal to 1 sum, at I equal to 2 sum, at I equal to 3 sum, and so on. Directly we get final sum. But in recursive procedures, intermediate results are also available in computer memory. Intermediate results. At first recursive call, what is the result? At second recursive call, what is the result? Like that, all the intermediate results are also available in computer. That's why at each recursive call, how much space is required? At each recursive call, how much space is required? Anyway, we decided how many recursive calls are there? N plus 1 recursive calls are there, because at n we are calling recursive procedure, at n minus 1 we are going to call recursive procedure, at n minus 2 so on. 1 also we are going to call the recursive procedure, but after n value becomes 0, means once after considering all the elements, again we need to repeat one more time for knowing that there is no element remained. So totally n plus 1 times the recursive procedure is called. But the question is, how many cells are required at each recursive call? I have already explained now in variable part. The recursion stack is depending on 3 parameters. See here, one is n. Second one is a of n. Third one is return. Local variable, formal parameter, return address. What I told, 3 parameter values: formal parameter, local variable, and return address. Only these 3 parameters are appearing in this recursive call. But next time, if recursive call is made next time, then that one becomes n minus 1. Here we need to extract a of n minus 1. Again we need to return the result. Next time this n becomes n minus 2. So every recursive call we need to store n value, a of n value, result. Next recursive call we need to store n minus 1, a of n minus 1, return. So like that, at 1 also we need to store 1, a of 1, return also. So that's why at each recursive call 3 cells are required minimum. Each recursive call 3 cells are required. One is for storing either n or n minus 1 or so on, 1 or 0. Another cell is used for storing a of n or a of n minus 1 or a of n minus 2 or a of 0. And finally, return also required one cell. That returns the result back to memory. Is it clear now? So totally, this simplest recursive procedure, each call is requiring 3 cells, and the number of repetitions are n plus 1. Then the space required by this recursive call is SR sum of n is equal to 3 into n plus 1. This 3 into n plus 1 is the total space needed by this simplest recursive call. But we don't know how many recursive procedures are there in the program, and how many cells are, how many statements are repeated, how many arrays are involved in this particular recursive procedure. That's why we can generalize this as simply put greater than or equal to. This is the This is the relationship. This is the relationship, and any recursive procedure array sum is requiring minimum 3 into n plus 1 cells. Minimum 3 into n plus 1 cells. So this is the minimum. Okay. So is it clear up to this? One is simplest program. Simplest program, there is no variable part. But in simple iterative procedure, where the problem instance is characterized by n, problem instance is characterized by n. So based on n only, array size is varying. So that's why array is requiring minimum n cells. That is known at running time. So that's why that n is coming under variable part, and these three cells are coming under fixed part, because these cells are three simple variables are there involved in program. Those simple variables are requiring one cell each or one word each. But in recursive procedure, this is different from iteration. But in iteration, we cannot collect individual or intermediate results. Finally, we gather final result here. But the beauty of recursion is which stores all the intermediate results also, including parameters. So that's why we need to identify how many cells are required at each recursive call. That is first parameter, and how many times this particular recursive procedure is repeated. If you gather these two items, just multiplication is required. So each recursion is requiring three cells or three words. Like that, the number of recursive calls are n plus 1. Then 3 into n plus 1 is the total space needed by the simplest recursive procedure. But this is simplest. What do you mean by simplest? One recursive call, one array, one statement under true and false. But we cannot expect always such type of statements. So that's why generalize this condition as space required by any recursive procedure with n elements is greater than or equal to 3 into n plus 1. So this is about space complex standard performance analysis. In next video, I am going to explain time complexity. Thank you so much.